classification system, right? You only have pictures of so many people in your database from so many angles, but obviously A, more people are out there, and B, more people are going to be born each day who bring their own faces to the world, right? And you cannot possibly train on all people. But what you can do is you can generate random faces, so to speak, and use those to augment your training data for your facial recognition machine. Okay, and now let's look at the computation graph, right? So now we're going to put the mathematics and the actual implementation together. So we're going to start out with an observation X, which again might be an image in this case. And we want to get back to X, right? So we want to reconstruct X. And that is basically going to be the encoding up to Z and the decoding part from Z to X. And I've colored X in here because it's going to give us the joint density over Z and X, which was part of our objective. So we actually need that in order to compute the elbow and derive gradients with respect to the elbow. In general, I'm going to color all nodes that are related to the objective in blue. Okay, so what's happening here? So we're going to use X and use the variational parameters lambda that we assume have already learned, or at least learned up to a certain level. And we're going to infer what? A mean mu, a Gaussian mean mu, and a Gaussian standard deviation sigma. And why would that be a Gaussian mean and a Gaussian standard deviation? Well, remember what I said, right? Generally, we're using Gaussian approximations. And we could potentially use other approximations. I'm going to use a Gaussian approximation in this case, just because it's the easiest thing to do, and it's actually what most people do in most applications, right? So more often than not, our variational approximation will be Gaussian, and that's exactly the example that we are going with here. So we are computing the variational mean mu and the variational standard deviation sigma using our variational parameters lambda. And I'm being deliberately vague here about what these variational parameters lambda are, but they might be maybe anything at all. And in particular, in the variational autoencoder, they're going to be neural networks, right? So this might be a feed-forward layer, that might be a full-blown ResNet, because we're dealing with images, right? So a ResNet would make sense here. Any architecture that you can think of, really. And the parameters of that architecture, I'm going to collectively call them lambda. Okay, so now once we have the variational mean and variance, we somehow need to compute Z from them. Or rather, we need to sample Z from them. And this is where our trick with the introduction of the variable epsilon comes in. So we're now going to introduce epsilon. Sorry, I should have said that this thing here is generally called the inference model, and this thing here is called the generation model. So as I said before, the inference model encodes the observation X into latent variable Z, and then the generation model decodes it from the latent variable Z into an observation. But what we are concerned with now is mapping this variational mean and standard deviation to a sample of Z. And this is where the mapping from epsilon comes in. So I told you need to find a transformation from a standard normal distribution to your target, to your variable of choice, to your variational approximation. And it turns out that for Gaussians, that is particularly simple, because to transform a standard normal distribution to any other normal distribution is simply done by taking the mean and adding the standard deviation times a sample from a standard normal distribution. Okay, and that's how we'll get Z here. Notice, however, that because epsilon, the sample, is kind of hanging around on the edge of the computation graph, we can compute all gradients fine. So in particular, we're going to have gradients flowing back from our loss function all the way to Z, and then through mu and through sigma, all the way back into our variational parameters lambda. If we sampled Z directly, right, gradients of samples are, nobody can take gradients of samples, right? So basically the gradient flow would stop here, and we would never be able to update our parameters lambda. And that's exactly what we've seen in the theory section. If you remember, we were able to compute the derivative with respect to theta just fine. It was the derivative with respect to lambda that was giving us trouble. It's the same here. If we were to draw samples of Z directly, yes, we could still compute the parameters with respect to theta. We would not be able to compute the parameters with respect to lambda. However, because we did the variable transformation trick and because the sample is now at the edge of the computation graph, gradients can flow through this computation graph nicely, and we get all the gradients that we need to update both our model parameters theta and our variational parameters lambda. Have I forgotten anything? Well, yes, I have. We still need to have the entropy term, which again contributes to our loss term. That's why I've colored it in blue. And it only depends on the standard deviation. So that's just a fact of Gaussians, right? So the entropy of a Gaussian only depends on the standard deviation, not on the mean. For other variables, that may be different, right? So there may be a variable where we also need to condition on the mean in order to compute the entropy. And finally, I told you that we need a determinant in order to correct for the volume expansion. As it turns out, and I'm not going to go into any details here, if we are mapping from a Gaussian to another Gaussian, so in this particular case, if we are mapping from a standard normal distribution to any other normal distribution, the entropy term actually, the determinant term actually cancels. So in this particular case, and this is another reason why this Gaussian approximation is so well loved among practitioners. In this particular case, we don't actually need the volume correction term. We don't need the determinant. Once the transformations become more complex, we will need the determinant term. And I just encourage you to look at the ADVI, or Automatic Differentiation Variational Inference paper, to read up more on that, right? But whenever you're using a Gaussian approximation, that is all you need. So you'll have your loss with respect to the joint over X and Z, and you'll have your loss with respect to the entropy, and that's going to be it. Okay, now I also want to show you some code that is actually available on GitHub for how you would actually implement that. Notice that this is implemented in MXNet, so don't get too hung up on the details. I really just want to get you like the rough idea of how you would code this in Python. So what we're going to have is we're going to have an inference net, which, given some data, computes the mean and standard deviation of the Gaussian. We're also going to have some sampling method that takes the mean and standard deviation as input and gives us a latent state. So that is basically where we are generating from a standard normal distribution, applying our transformation, and then we get our latent state, which would correspond to Z in the graph, right? So the latent state is the same as Z. And then we're going to have what I call KL loss here, because it has a slightly different formulation of the L, but think of it as the entropy, right? So that's the entropy loss. And we're going to have the log likelihood loss, which is basically a loss on the reconstruction X, right? That basically tells us how well or badly we have managed to reconstruct the observation, the input image X. And in the end, we're just going to group these losses, and what MXSim group does is it just adds them up, right? So there's literally going to be the joint density of X and Z plus the entropy term. Let us look into some of these a little more closely. So in particular, in the train method, we're just gonna, so this is actually for pixel generation, where the pixels are binary. So this is just basically computing the loss with respect to X and Z, so the likelihood with respect to X and Z. In this case, it's a Bernoulli likelihood. It might be anything else, right? What's more interesting is the sampling of the latent state. So up here, we have some bookkeeping related to reshapes and dimensionality, which is really not something you should worry about at the moment. The main thing is that how we map the standard normal variable epsilon to our variational approximation Z is, as I've said before, we take the mean and add the standard deviation times a standard normal sample. So in particular, this part here, the draw from a normal distribution with location 0 and scale 1, that's epsilon, right? So really it's just mean times standard deviation. Sorry, mean plus standard deviation times epsilon. Okay, so yeah, that's basically the core of the implementation. And as you see, it's one line. So although we went through quite some heavy math and we did quite some heavy lifting on the theory side, surprisingly and nicely enough, what we end up with is a one-liner. And that's also why I said in the beginning, it's a general purpose algorithm that's pretty straightforward to implement. Some concluding remarks on variational inference. There are some practical considerations. In particular, oftentimes we make a mean field assumption, which really just means that the posterior or approximate posterior factorizes over its dimensions. If we think of Gaussians, all this means is that your covariance is going to be diagonal. So instead of having a full covariance, we're going to use a diagonal covariance. It's just a simplifying assumption, which in particular in the case of Gaussians is mostly for memory considerations, because if you're dealing with really big models and you have lots and lots of latent variables, each of which has like a high dimensionality, then storing full covariances for these, which would basically have the dimensionality of the variable squared, is just not feasible in terms of memory. So that's why we usually assume that the approximating Gaussian just has a diagonal covariance. That limits our approximation, obviously, because if there's covariance structure in the true posterior, again, we're not going to be able to capture that. And another practical consideration is that the KL divergence tends to, or the optimization of the KL divergence tends to underestimate posterior variance. So if you get really small variance with your variational approximation, chances are that the variance of the true posterior is actually larger than that. So if you're in doubt whether you should trust your variational approximation on the posterior variance, probably not. The true posterior variance is probably going to be a little larger than what the variational approximation gives you. Further topics to read up on are the Gumbel softmax. So that's being used for discrete variables, right? So far we've only been talking about continuous latent variables, so particular Gaussians. If you want to use discrete variables, you may want to look at the Gumbel softmax. And there's a whole other way of doing variational inference, where instead of this mapping from one variable to another, you're doing something entirely different. And that's called the score function estimator, also known as reinforce. And the best paper, in my opinion, to present that idea is Paisley et al. 2011. So that's definitely something worth looking into. The advantage of the score function estimator, it's harder to implement. It comes with all kinds of separate problems. The advantage is that it handles both discrete and continuous distributions effortlessly. So instead of having to think up something like the Gumbel softmax trick, which handles discrete variables in the case of reparametrization, so in the case of the method that we have just seen, the score function estimator just handles all of them effortlessly. Comes at the price at being a little bit harder to implement and needing more fine-tuning. And another topic that you may want to look into that's very dear to my heart is normalizing flows. So we've talked about how oftentimes the posterior will have weird shapes. Like, for example, it may have 2 or 3 or 5 or however many humps, and you're approximating that with a Gaussian. Because the Gaussian only has one hump, your approximation is going to be bad. We've also said that generally you don't know what the shape of your posterior is going to look like. So basically, when you're choosing your posterior approximation, you're kind of fishing in the dark a little, right? Yes, you're going to use a Gaussian because it's a simple thing to do, but really you have no clue what your posterior looks like. Normalizing flow are learned posterior approximations. So instead of saying my posterior approximation is definitely going to have a Gaussian shape, normalizing flows allow you to say, I have no clue what my posterior looks like, so let's learn the posterior shape along learning the variational parameters. And normalizing flows allow you to do that. They're a very powerful tool, but unfortunately they're a bit outside of the scope of today's lecture. All right, that was everything I want to say about variational inference. Now let us move on to Markov chain Monte Carlo methods. Just as a reminder, Markov chain Monte Carlo, in comparison to variational inference, it is more precise. It will give you samples from the true posterior if you draw enough samples. But nobody really knows what enough means, and you may just spend a long, long time sampling from the posterior. Yeah, so that's the trade-off here. So Markov chain Monte Carlo is going to be a more precise, more accurate method that unfortunately, though, you won't really be able to apply in many practical scenarios just because it takes a long time, and especially if you're dealing with big data, it's just not going to be feasible to run it for long enough. However, if you're dealing with medium-sized data, where when I say medium-sized, we are talking maybe 100,000 images, Markov chain Monte Carlo might actually work really, really well. So what's the idea behind Markov chain Monte Carlo? Well, before we skip to Markov chains, I'm just going to tell you the Monte Carlo part. So Monte Carlo is actually the capital of Monaco, which is a dukedom at the south coast of France. And that dukedom is known for one thing, or two things actually. It's a tax haven, so lots of rich people go there to evade taxes. But also it has a casino, and the Casino of Monte Carlo is well known, has featured in several James Bond films, amongst others. And that's basically where the name of Monte Carlo techniques derives from, because Monte Carlo techniques depend on randomness of the outcome, just as gambling has a lot of randomness in it, obviously. Okay, and to give you a feeling for what for what Monte Carlo methods are doing, let's look at the following image. So we have a circle, right? And what we want to do is we want to approximate the area of that circle, where the area is pi, right? Okay, so computing pi exactly is basically impossible. I don't think there's a closed formula for pi. So all we ever can do is really approximate what the size of pi is. And the way we're going to approximate that is as follows. So we have the circle here, right? That's the blue line. And do you see these dashed lines around the circle? So we're just going to focus on the lines ending in 1 and -1, right? And then you can see that what we actually have is a square around the circle, where the square and the circle are touching at 0. Yeah? And drawing samples from a square, uniform samples from a square, is relatively straightforward because, well, I know the area of a square, I know how to compute that. And once I know how to compute the area, I can just easily draw samples from that area uniformly, right? So, and that's exactly what I'm going to do. So I'm going to draw uniform samples within that square. Okay. And in this first instance, I've drawn 10 samples from the square. And as you can see, 3 samples are outside the circle and 8 samples are inside the circle. Now, what I need to do in order to find pi, which is the area of the circle, is I basically know what the area of the square is. It's 4, so 2 by 2. And I just need to check how many of the points are inside the circle and how many are outside the circle. And this fraction, the number of points inside the circle over the number of points times 4 is going to give me an approximation to pi, because 4 is the area of the square, and I'm going to have a fraction smaller than 1 of points that are inside the circle. So in this case, as I said before, I think there's 3 points outside the circle. So inside the circle are 7 points. So 7 over 10, or 0.7 times 4, is going to be my approximation to pi. So in this case, it's 2.8. If you know the value of pi, not a great approximation, not really. So what can we do then? Well, as I said before, in Monte Carlo techniques, the more samples you draw, the more accurate you're going to be. So instead of drawing 10 samples, let us draw 1,000. As you can see, they're like very evenly distributed across the square, which is good. That means we are sampling correctly, uniformly from the square. And again, we're looking at how many points are inside the circle, how many points are outside. I can't really tell you how many. I just know I've defined this function here that basically computes this fraction for me, right? And basically looks at how many points are inside the circle. And if we multiply this by 4, the area of the square, what we get is 3.104. Much, much better approximation to pi. Still not exactly great. So let's draw 100,000 samples instead. And I'm going to warn you, I don't have a picture for the 100,000 samples because all you'd see is orange, right? So the circle would be completely overwhelmed by the dots that we're drawing from the square. But basically, if we draw 100,000 samples, our approximation to pi is this here. And then if we look at the exact number of pi, we're pretty close. We're actually hitting it up to the third digit after the comma, right? And that is the magic of Monte Carlo. The more samples that you draw, the closer you are going to come to the exact value. And in particular, if instead of drawing 100,000 samples, we drew 100 million samples, chances are we'd be hitting pi very, very exactly. Okay, and that is exactly what we're going to do with our posterior. So instead of approximating the posterior with another distribution, no, we're going to draw samples directly from the posterior. And now you may say, but wait, how do we sample from the posterior if we can't even compute it? So let us turn back to the original problem of Bayesian inference, namely that we can't compute the posterior exactly because we can't compute P of x, right, the marginal over x, our data. And I'm going to call x the reference density here, because what it does essentially is it normalizes the joint density over z and x, right? So now, what if we could swap out this reference density, which we can't compute, for another density, which you can actually compute? That's kind of the underlying idea here. And the way we're going to do that is by approximating, again, that reference density P of x that we can't compute. How are you going to approximate it? Well, let's look at P of x. What is it actually? Well, it's a marginal over z when we take the joint of x and z. And what we're going to do now is we're going to introduce another reference density Q of z, which we can compute by design, right? We're going to choose a density which A, we can compute, and B, that we can sample from. However, we can't just introduce that new density as a reference density. What we actually have to do is we multiply the joint density Pxz by 1, where 1 here comes in the disguise of Qz over Qz. And what that gives us is an expectation over this ratio Pxz over Qz. And just as we did for variational inference, we're going to approximate this expectation using Monte Carlo, so sampling. And there's one crucial difference to what we did in BI. So in BI, I said often one sample, maybe 10 samples is enough. Well, here we'll actually have to draw a lot of samples. So we're kind of in that scenario with the circle and the square, right? Where in order to approximate the area of the circle correctly, we need to draw lots of samples from the square, and it's the same thing here. So in order to approximate Px closely, we'll need to draw a lot of samples, possibly thousands of samples from Qz. But the good thing is two things. So first of all, this is going to give us an unbiased estimate, meaning we're going to recover Px exactly if we're drawing enough samples. Well, again, in practice, we'll just have to limit ourselves to a finite number of samples. But also, we don't need Px anymore, right? So we're actually approximating Px through sampling from another reference density. So that's good news, because it, again, removes this limitation that we have of not being able to sample from Px. There are a couple of limitations here. So first of all, we're only computing a density, a marginal over x. But really what we care about most of the time is like some statistic of the posterior, right? Where the posterior is z and x is just the data that we have observed. Now, there is a technique called importance sampling, where we're actually using this ratio Pxz over Qz for each sample as a weight. And then as we compute the statistics, we'll just compute the statistics over our samples of z. But each sample is weighted according to this ratio. So that will then, actual importance sampling is a bit more complex than that, but the main idea is that the samples are weighted by this ratio here. And that will then give us or allow us to compute sample-based empirical statistics over the posterior. However, there are several problems with that technique, and that's why we'll actually add on Markov chains to the Monte Carlo methods. But let's first review the problems that we have when we're just using these weights, right? Either to compute the density, the marginal of px, or in order to weight samples. Well, the density is basically the following. Again, just as a variational inference, q of z might be badly chosen. And if that is the case, the weights will be very far apart. In particular, one sample might dominate all the others simply because it has a high weight and all the others don't. So if we here assume that the density, our target density, the posterior, would be the small circle, the orange circle, and our proposal density or reference density is the blue circle, then the following is going to happen. Most samples are not going to be anywhere close to the actual posterior, right? Meaning they'll receive very, very small weights. And then the one or two samples that hit the posterior will receive high weights. And that does two things. First of all, are these samples that receive high weights representative for the statistic of interest? We don't know. But second, it will introduce a lot of variance, right? Because there will be variance in the weights. Lots and lots of weights will be very small. There are some weights that will be very high, which means overall, if we take the variance of all samples, or rather over the weights of all samples, we'll get a very, very high variance, which then again means that our estimator, that sample-based estimator, becomes very unreliable. And I'm showing you this here in just 2 dimensions, right? And there you can kind of see, if we choose QZ badly, then we have very little chance of actually hitting the posterior. It's even worse in high dimensions. So now if you imagine this problem in like 100 dimensions, 1,000 dimensions, it gets exponentially worse, right? Because the volume that we're dealing with is much, much larger than what we see here on the 2D picture. So basically, for most practical applications, and if the shape of the posterior is somewhat complex, we can't really apply this technique. We have to do something else. And that something else is, instead of drawing independent samples, we'll try to draw correlated samples. And we'll do that through Markov chains. So Markov chain Monte Carlo will give us correlated samples, which has the drawback that the samples are not independent anymore, and therefore we can't really count them as like 2 independent samples, right? Turns out it's not too much of a problem. All it means is that we have to draw even more samples, because until we get from a sample to another sample where they're truly uncorrelated, we'll have to pass through a wide, depending on how well your sampler works, but potentially we'll have to pass through a long line of correlated samples until we get 2 samples that are actually uncorrelated. So Markov chain Monte Carlo allows us to alleviate some of the problems that we are facing with just that naive sampling strategy that I showed before, but we'll have to draw even more samples. The nice thing is that we still have the convergence guarantees, so if the Markov chain is constructed appropriately, then again, we'll still recover the posterior exactly, or samples from the posterior at least. And what does it mean to do Markov chain Monte Carlo instead of Monte Carlo? Well, it's simply a change in the reference density, where the Markov assumption just means that each sample depends only on the previous samples, but not the samples before, right? So if I'm drawing 1,000 samples, and I'm drawing the 1,000th sample, that sample will only depend on the 999th sample, and not the other 998 samples, right? So yeah, our reference density will now always condition on the previous sample that we drew before. And there's a classic algorithm called the Metropolis-Hastings algorithm that accomplishes exactly that. So that allows us to define a Markov chain and then move from sample to sample. And its ingredients are basically as follows. So at each point, we draw a new sample from the conditional distribution that conditions on the previous sample, and then compute an acceptance threshold, where I don't really want to go into the details of the acceptance threshold at the moment. Just notice that it basically gives a threshold for whether or not to accept the sample, right? And then we basically draw from a uniform distribution between 0 and 1. If our draw is below the acceptance threshold, then we'll accept Zj as a new state. Otherwise, we'll reject that current proposal Zj and use the previous sample instead. So notice that that means that although we're transitioning from sample to sample, autocorrelation between the samples, I said before, right, the samples are not independent anymore, but they're correlated. Autocorrelation between these samples may be perfect. Namely, in the case that we reject the new proposed sample and just keep the old one, because then two consecutive samples will be identical, right? And until we accept a new sample, we'll just stick with this one sample. Which again also means that if this conditional distribution is badly chosen, right, and you are constantly rejecting samples, you'll just stick with this one sample all the time, which of course will not give you a very good representation of your posterior at all. So that's why it's important to choose a conditional distribution that actually allows us to transition quickly and draw as many different samples as possible. And I'll show you an algorithm that accomplishes that very, very well in a minute. But let me first help you visualize how Markov chain Monte Carlo actually works. So generally, we'll start out somewhere in space because we need to initialize the algorithm somehow, right? So we'll initialize it with a random sample. And then let's assume that this red line over here is our posterior, right? So our posterior happens to be this weird shape, kind of like almost rectangular, with a hole in the middle. So then we start out somewhere randomly in space, and what the Markov chain algorithm does for us, or Markov chain Monte Carlo algorithm does for us, is it moves us closer to the posterior. And then once it hits the posterior, it stays there. So then it starts moving around, and you can see that all of these samples are actually on the posterior. The important bit here is that it actually may take quite some time to hit the posterior. And obviously these first couple of samples are not representative of the posterior because, as you can see, they're not really lying in the posterior. So again, it is important to draw a lot of samples in that scenario because eventually, if we're drawing enough samples from the posterior, they'll just overwhelm these other couple of samples that are not part of the posterior, so that effectively we can neglect these first couple of samples, right? But in order for that to happen, obviously we need to draw enough samples from the posterior. So we need to stay inside the posterior for long enough and sample inside the posterior for long enough. So again, running the Markov chain Monte Carlo sampler for long enough is crucial at that point. So now let us look at a state-of-the-art method for Markov chain Monte Carlo. So actually, I presented Metropolis Hastings to you because it's like the classic thing to do, and there's some elements of that you'll even find in Hamiltonian Monte Carlo. But Hamiltonian Monte Carlo really is the state-of-the-art algorithm for sampling. And it makes sampling much, much more efficient by basically allowing for faster and wider transitions between samples. So two things. The algorithm is going to be faster as such. Why is it faster? Because it basically makes bigger jumps. So the distance between two adjacent samples is going to be large compared to Hamiltonian Monte Carlo, compared to Metropolis Hastings. So as I said before, worst case scenario would be that we never move, right? We just stick with this one sample. Well, what Hamiltonian Monte Carlo is going to do for us, it's going to not only move us away from the sample, but it's going to move us away from the sample very, very far. So that in the end, also, although it's still Markov chain Monte Carlo and samples are autocorrelated, that correlation may pretty much vanish because we're taking such large steps. And that also means that we're rejecting very, very few samples. It may still happen that we're rejecting samples, but by and large, we're going to reject very, very few samples. And I strongly encourage you to check out Michael Betancourt's Introduction to Hamiltonian Monte Carlo, where he really goes into a lot of depth and detail. And actually, the next couple of plots are from that paper. I'll somewhat gloss over the mathematical details here because it gets quite complicated, and just try to give you an intuition for how Hamiltonian Monte Carlo works. So, as I said before, Hamiltonian Monte Carlo, or the goal of Hamiltonian Monte Carlo at least, is to take us further. So, whereas with Metropolis Hastings, we saw all these dots that were scattered along the posterior, and they were very close to each other, what we're trying to do with Hamiltonian Monte Carlo is we're going to try to move very far. So instead of having adjacent samples being literally adjacent, we want to have them as far as possible apart from each other. And why? Well, we want to explore all areas of the posterior. We want to get a representative sample. The most efficient way to do that is to just move as far as we can, because thereby we'll ensure that we're in a completely different space of the posterior. And even if we're not drawing a whole lot of samples, say even if we're only drawing 100 samples, because we have explored so many areas of the posterior, and that'll actually help us get a better summary of what the posterior looks like. So it's called Hamiltonian Monte Carlo because it uses Hamiltonian dynamics. What are Hamiltonian dynamics? Well, Hamilton came up, or rather, Newton came up with the thermodynamic laws, and those were later on formalized as Hamiltonian dynamics. And Newton's second law, what does it state? Well, it states that energy can't evaporate, right? So whatever you do, whatever physical movement you do, whatever physical activity is happening, energy can help change the state of matter from one state to another. So think, for example, of water. If you cook it, so if you add energy, it'll turn into steam, right? So that's what's happening. But the overall amount of energy that's there never changes, right? So if we're thinking about a closed physical system, and that closed physical system being your kitchen, the overall energy in your system doesn't really change. And that's what we are going to exploit in Hamiltonian dynamics. So we're going to have Z as a position variable. And remember, Z is our latent variable that we're trying to do inference over. And we're going to have U called a momentum variable. So the position basically tells us where we are in the space. So think again of our posterior as a wiggly surface, right, with lots and lots of humps. And Z is the position variable, which basically tells us how high up these humps we are. And the humps are obviously just the density of the posterior. So if we are high up on a hump in the posterior, that means we're in a high probability region of the posterior, and that means that we have high position, right? Whereas if we're in a valley, we're in a low probability region of the posterior, then we have low position, right? And momentum basically gives us two things. It gives us direction, and it gives us speed of travel. So basically, say we're in a valley, and we're surrounded by two humps, right, by two mountains. Now there's two decisions that we need to make. Which direction do we want to go? Do we want to go up the left hump, or do we want to go up the right hump? And the second decision that we need to make is, how fast do we want to go, right? And that's basically what the momentum variable tells us. So momentum is direction plus speed. And notice that momentum is crucial to actually get onto these humps, because if I don't have enough momentum, basically if you think of a little ball that's rolling up a hill, if it doesn't have enough momentum, at some point it'll stop and it'll reverse and roll down that hill again, right? So if we actually want to get into high probability regions, we need some momentum, or sufficient momentum, in order to get up these high probability regions. So how is the Hamiltonian function made up? What is it made up of? Well, once we have the joint density as before, and that will basically, again, give us a measure for the height in our posterior. And notice that, again, we don't need the normalizer here, right? Because the normalizer doesn't really do anything for us. It doesn't change the shape of the posterior, just normalizes it, right? Whereas here, we just care about the height. And whether that height is scaled or not by the normalizer doesn't really interest us. So that's why we can actually neglect the normalizing constant p of x here. And then we have to define the momentum variable. And usually the momentum variable is chosen such that it depends on the position. Doesn't need to be, could be chosen independently. And in fact, it's often chosen to be standard Gaussian. So in that case, it might just be chosen independently of z, right? So if we choose PUZ to be independent of z, and then we could just assume it's a standard Gaussian. And again, for practical purposes, that's often done. Now you can optimize your momentum variable, but again, we're going to stay with the simplest variant of the algorithm, and we're just going to draw from a standard Gaussian here. Okay, then what's actually happening? So notice that we do not really care about the momentum variable. It is a useful tool, and it enables us to simulate Hamiltonian dynamics, but we're not interested in it. What we're interested in is the posterior, and in particular drawing samples from the posterior. So we are interested in getting samples from Z. What Hamiltonian Monte Carlo does then is the following. So unfortunately here we have P and Q on the axes, but because I took this from Michael Benancourt's paper, but really what it is P is our U and Q is our Z. So we want to move in Z space, right? That's what we're interested in. We want to generate a new sample from Z. And remember that the difficulty of moving in Z space lies exactly in defining a good proposal distribution that will get the next Z sample accepted, and at the same time moves a long way so that we don't have Z samples that are very close to each other and highly correlated, right? So how does Hamiltonian Monte Carlo achieve that? Well, at any given point Z, right, at any given position, we're going to sample a momentum variable, which means we're going to sample a direction to go in and the speed at which we're going, okay? And that's our U variable. So we're saying, so the technical term is we're lifting Z into UZ space, right? So Z space is one-dimensional. U space is also one-dimensional. UZ space is this whole thing here, it's this whole plane, and it's two-dimensional. So we're lifting Z into UZ space, and then using Hamiltonian dynamics, we travel in joint UZ space for a given period of time, and then we project that UZ sample, that joint UZ sample that we get, down to Z space. And just as lifting simply means we are sampling randomly from U, projecting down to Z means we're just throwing away the sample of U at that point, and all we're left with is a new sample of Z. And because we're using Hamiltonian dynamics, and because U and Z together make up an energy function and energy stays constant, right? The probability that we get another sample Z that is in the posterior, although we have traveled very far in the posterior, is very high, which means the acceptance probability is also very high, right? So the whole trick here is really by moving through joint UZ space, we are able to generate a new sample that has very, very high probability of being accepted. And what we've achieved is that A, we have high acceptance rate, so our samples are actually different, and B, not only are they different, but they're also very far apart from each other, thereby reducing autocorrelation. Now let us look at how Hamiltonian Monte Carlo can be implemented. Just as with variational inference, although there's quite some heavy mathematics involved, the implementation is actually rather simple. So what we're going to do is, at each point that we are advancing in UZ space, we're going to advance as follows. So we're going to first move half a step, or we're going to update U by half a step. Then we're going to update Z by one full step, and then we're going to do another half step of U. So instead of updating all variables jointly, as we did with variational inference, we're actually updating them one after the other. But instead of taking full updates for U, we're actually just going to take half updates for U at each point. And that has to do with just the convergence of the simulation of the Hamiltonian dynamics. But basically what I want you to note here is three things. First of all, this can be anywhere in any given step of the trajectory. So I told you initially that U gets sampled randomly, right? But it only gets sampled randomly once. We don't ever resample it. Or rather, we sample it when we want to generate the next Z sample. But while we are in one trajectory in UZ space, so while we haven't projected down to Z yet, while we're in this one trajectory in UZ space, we update U, but not by sampling, but rather deterministically by implementing these Hamiltonian dynamics. And then for each advance in U and Z, what we do is first we do a half update to U, full update to Z, and then another half update to U. And these updates are just defined by how Hamiltonian dynamics defines them. And in order to update U, we need to take derivatives with respect to Z. which again is going to be done for us by automatic differentiation. So even if we have a very complex model here, we don't really need to worry. Then Z is simply updated with the value of U. And again, then we update Z again with the gradient with respect to Z. Just notice that before we took the gradient with respect to the previous value of Z, and then the second time we take the gradient with respect to the current value of Z. And one more thing to note also is that we have epsilons here. These are not random samples, but rather they are, if you wish, our learning rate, or the rate at which we want the trajectory to move. So in particular, if epsilon is very large, then the steps that we're taking are going to be large too, and if epsilon is small, we're going to take smaller steps. And it's often preferable to take smaller steps. It means we'll have to take a couple more steps, but at least we'll get higher accuracy in the sample Z that we're producing, which again means we'll get a higher acceptance rate. So let me show you how this can be implemented in Python. So we have the step size epsilon, and then it's really just update y, so y is our u, update x, which is our z, and update y again, which is our u again. And that's already it. And how do we update y, or rather u? Well, it's exactly this. So we take the gradient with respect to the position variable, and this gradient here is just a black box function again, right? That's some automatic differentiation magic that is happening, and you don't really need to worry about that. And the update with respect to y is then the same thing, just that we're taking, the update with respect to z is the same thing, just that we're taking the gradient with respect to u. And you can see that all of this here can basically be automatized by exploiting automatic differentiation. So if you have the automatic differentiation routine for whichever model you're using, then the updates are very, very simple and very straightforward. Okay, further topics that you may want to look into when it comes to HMC is setting the step size, so the epsilon parameter for HMC, because setting it by hand can be a bit cumbersome, and there's actually ways to set it automatically. Moving away from HMC, or rather, let's stick with the topic of HMC. So another thing you may want to look at is the no U-turn sampler. So I gave you the very basic version of HMC that has its own problems. It still works pretty well, but it can be made even more efficient with something that is called the no U-turn sampler. So basically what it does is it avoids that the chain doubles back on itself. So in theory, say our posterior is a circle, right? Then if I take a very large step, it may happen that I still end up with highly correlated samples. And why? Well, because I went one time through the entire circle and ended up very close to my initial position. So what a no U-turn sampler does is it doesn't do any U-turn. So the moment it recognizes that the trajectory is doubling back on itself and in danger of hitting the starting point, it just stops the trajectory and takes the point that we're currently at as the new proposal for Z. Very interesting paper. I encourage you to look at that. More towards the general theme of sampling, something that is also worth checking out that I didn't talk about today is the Gibbs sampler. And why? Well, HMC requires differentiability of the variables, and it doesn't work very well for discrete variables because discrete variables are often not differentiable. So in that case, you may want to use the Gibbs sampler. So the Gibbs sampler is another, so different from Metropolis Hastings, different from Hamiltonian Monte Carlo, is yet another sampler that unfortunately is not very efficient, but works really, really well when you're dealing with discrete variables. Okay, let me finish up this section by talking about some applications. Now, all these applications can in principle use Hamiltonian Monte Carlo or variational inference, but I'm going to present two applications where sampling, not Hamiltonian Monte Carlo, but where sampling has been used. So one is the Netflix challenge. And this here looks very, very complex, but it was actually the winning model, I believe, and it's a Bayesian matrix factorization model. So what Netflix wanted to do is it wanted to predict ratings for movie customer pairs which hadn't really occurred, right? Because the problem is that most customers haven't seen most movies, right? So each customer maybe has seen 100 movies, but Netflix has thousands in its library. So how can it predict the ratings for customers and movies that the customer hasn't seen? Why would it want to do that in the first place is the question, so that it could recommend movies to new customers, right? Or to existing customers also, but basically recommend new movies that the customer hadn't seen yet. So they would basically try to extrapolate what hypothetical rating the customer would give to any given movie. Okay, so the rating is what we're trying to predict, and the model basically has a movie embedding and a user embedding. And the rating then is the result of a matrix multiplication between the user matrix and the movie matrix. And each of these has its own hyperparameters and its own priors. And why? Well, again, because most customers don't actually watch a lot of movies, right? So it's really hard to find a customer representation, a customer embedding that represents that customer well. So if I just joined Netflix and I've only seen 3 movies, you don't really know what my taste is, right? And you don't really know how you should represent me in that matrix factorization framework. And then the priors help to get information about customers that haven't seen a lot of movies, or about new movies, for example, that a lot of customers haven't seen yet, by sharing information between existing customers. So this basically says, if I am a new user, I haven't seen a whole lot of movies, Netflix doesn't have a whole lot of information about me, then they're just going to treat me very, very similarly to the average customer, right? So if you don't know anything about me, just assume my taste is that of the average person. That's basically what it's saying. And then incrementally, as I watch more movies and as I make my preferences known to Netflix, this customer embedding for me can then get updated accordingly, and can, if I'm not like the average customer, can move away from the average customer embedding. So that's basically the idea of the model, and their sampling techniques were used in order to do inference on the models and in order to infer the distributions over customer representations and over movie representations. Another very, very famous example where actually both variational inference and sampling methods have been used is topic modeling. So topic modeling is basically used for ordering text and also for genome sequencing, and basically any task where you have a lot of data but not a lot of structure, and you want to organize the data somehow so that at least you have some structure in your data, right? So basically, if I'm giving you a random genome or if I'm giving you a random library, your task is to somehow organize these thematically. And topic modeling achieves this as follows. It basically categorizes words according to their topic, where the topic might be something like arts or budgets or children or education, something along those lines, right? And once I know which topic a word is likely to belong to, I can then extrapolate to texts, right? Because texts are made up of words. And if a text contains lots and lots of words from, say, the arts section, I can then categorize this text as being about arts. Now, obviously, there is not all texts only belong to one category, right? So, for example, I might write an article about the economics of the arts business, which would mean that probably there'd be lots of arts words in there, but also lots of budget words. And that's the cool thing about topic models, because they're probabilistic. They allow you to make soft clustering, so to speak, right? So a text might be 60% in the arts section, but at the same time, 40% in the budget section, exactly because it is a text about the business of arts. So yeah, these topic models have been hugely successful, tremendously successful in all kinds of applications. Another example just comes to mind is social media analysis, right? You're some company and people are tweeting you, and you're literally getting thousands of tweets every day. So there's no way you're going to have your social media consultant look through all of them. But rather you can run automatic models, topic models being one class of models that you could apply, and categorize these tweets. For example, you might want to use this if they're positive or negative, if there's feedback that may help you improve. So yeah, these models are tremendously useful. And again, traditionally, variational inference and sampling methods have been used. And there was kind of this flip-flop. So it's interesting. It actually tells you about the development in research on inference methods, because initially variational inference was used for topic models. Then for a long time, maybe 5, 6, 7 years, it was sampling methods that dominated topic modeling, just because they gave better results, they were more accurate. And at the same time, the corpora that were used, so the text collections, weren't super, super large. So they were at a scale where you could still use sampling methods and get really, really good results. And these days, we are back to variational inference again. And why? Well, because the corporas have just become extremely large, right? If you want to do this on all of Wikipedia or even larger text collections, then sampling is just not going to scale. And that's why people have reverted back to variational inference, accepting a potential sacrifice in accuracy, but just needing to use variational inference because it is that much more efficient, right? And there it's nice because you see the history of algorithmic development, but on the other hand, it also gives you an intuition for when to use sampling or variational inference. So variational inference, when you have huge text collections, go for variational inference. If you have smaller text collections and you can afford to wait a little longer and want really, really accurate results, then you're much better off using sampling methods. All right, at this point, it's my pleasure to thank you for attending. I hope you have lots of questions now that you can ask us afterwards. But let me first summarize what we've learned today. So first, we have learned about probabilistic graphical models, and they enable a couple of things. They enable you to specify the structure of the problem, so any real-world knowledge that you have about how the problem is organized or how the variables involved in a problem relate can be used in model building. And they allow for uncertainty estimation. So instead of saying, as I said before, right, a text belongs 100% to the arts category, no, it may belong to the arts category to some degree, it may belong to the budget category to some degree, right? And that uncertainty estimation is crucial. And in particular, you may be able to average over uncertainty. So that's very interesting when you're looking at posterior uncertainty in particular, if we think back to the variational autoencode example and the phases, right? Yes, you can draw particular phases and particular realization of phases, but maybe you also want to ask the question, what does the average phase look like? And in that case, you can just average over all latent representation and kind of get like the average phase that's somehow representative of the input data, of the input images you've seen. Probabilistic graphical models allow you to reason about parameters. So again, that goes back to the Netflix example where our parameters were the embeddings for customers and movies. And instead of just choosing fixed embeddings, we can actually have uncertainty about the embeddings themselves, and we can reason about them. And in particular, we can say something along the lines of, if I have very little information for this customer, I may not be able to produce a good embedding, so rather I'll make his embedding very, very close to the average embedding. And then finally, another application of probabilistic graphical models is causal inference, which unfortunately we didn't have time to cover today, but that is basically simulating experiments, right? Where usually you would do a drug trial on a control group and a treatment group. You may not always be able to do that, right? So for example, if you look at experiments with potentially fatal outcomes, you can, for ethical reasons, just not afford to actually have a treatment group because, well, chances are the treatment is going to kill people. So what you're going to do instead is you're going to look at observational data. So historical data where people, by accident or by force of nature, have either gotten a treatment or not gotten a treatment, and basically try to draw the same inferences that you would with experiment. Try to draw the same inferences from observational data. And that is something that you need probabilistic graphical models for as well. Then in the second half of this tutorial, we've focused on inference and learning. And we've seen that inference in general is harder for probabilistic models than just simply maximum likelihood learning. That's kind of the bad news. The good news is that there are some general purpose algorithms that work very well for most problems. And these are automatic differentiation, variational inference, and Hamiltonian Monte Carlo. You have seen those and can probably by now implement them yourself just by going through the slides again and basically copying and pasting the lines of code. but there's also many implementations around. So your time is probably more wisely spent on actually developing models and just using the packages that provide implementations of ADVI and Hamiltonian Monte Carlo. There's yet another piece of good news, namely that probabilistic inference is an active topic, very active topic of research. So once you start getting into that a little more, if you're interested, you'll see that there are lots and lots of improvements on these algorithms, and that by really understanding these algorithms and digging a little deeper, you'll get massive speed-ups and massive performance improvements when you're using approximate inference algorithms. All right, so that's it from my side. Again, thanks a lot for attending. I hope you got something out of it. And if you have any questions, then we'll be around, and please feel free to ask your questions. Thanks a lot and have a good day. Bye.